Hi everyone. I just held the Zoom class and I know that in the recording there's just going to be enough problems that I just decided to re-record what I presented to the class today in Zoom. So let's get started. So the t-distribution is what we're using this week because we do a t-test when we don't know the population standard deviation. In this one sample t-test that we're going to do, we know the population mean, but we don't know the population standard deviation. So the t-distribution is a little bit different than the z-distribution. It has thicker tails. You'll notice that right here. The t-distribution has the dotted lines. The tails are thicker. What you'll also notice is that with the t-distribution, the significance area is smaller. The cutoff point needs to be more extreme. There's more scores in the tails, and that's what we have to do. This means that it's harder for the sample mean to fall into the significance area. And so the reason is because we estimate the population variance, it has to contain some error. So mathematically, the test is more significant or stringent, excuse me. So just keep this in mind. The t-distribution is flatter. It has thicker tails, but it becomes more like the z-distribution as the n increases. So if we have a larger sample size, our t-distribution is going to look very much like the z-distribution. Think of it this way, the t-distribution approximates the z-distribution. It becomes more like the z-distribution with larger sample sizes. So this week, when we're talking about our standard error, I just want to step back and say that we no longer know the population variance or standard deviation, we have to estimate it. So I'm going to remind you of how we estimate the population variance based on a sample. And sometimes we just call this sample variance. Remember that populations have more variability than do samples. And so we use this degrees of freedom to correct this slight bias. So our sample variance, the formula for that is sums of squares divided by the degrees of freedom. And remember that the degrees of freedom in this case is n minus 1. So our sample variance is very much like the population variance, but with just this little adjustment here. And our sample standard deviation is just the square root of that. So this is similar to what we've done with the population variance, but this is an estimated variance for the population based on the sample. This time for a t-test, just like we did with the z-test, we're estimating the standard error. But this time we're substituting the sample variance in, and we're going to estimate that variance based on this in the population based on the sample we have. So all this is to say we have new notation for our standard error, which is S subscript m. And last week we did the variance divided by the square root of n. This time we're doing the sample variance divided by n and taking the square root of it. You could have the sample variance divided by the square root of n. It's the same thing, but this week we're demonstrating it this way. So just make sure you have this in your notes, that the estimated standard error is the square root of the variance divided by n, the sample variance divided by n. So here we go. I'm going to help you now with some of the more heady problems in the assignment, and I'm going to show you how to work these out. These next couple ones that I'm going to do require algebra, okay? So we can do this. The first question is: a sample has 25 scores, a mean of 38, and an estimated standard error of 5 points. What is the sample variance? So this is a missing piece type of question. So I'm going to draw this out for you now. Okay, so for this, I'm going to start with my formula for the standard error right here. And I'm going to plug in all those things that we know. We know that the standard error is going to be 5. And we know that the n is 25. But we don't know this variance. So we can figure this out. As I look at this, I know that 5 on this side is going to have to be equal to 5 on this side. So first thing to do is to figure out the square root of what is going to give us 5. Well, the square root of 25 is going to give us 5. So the next question is, how do I get 25 in under this square root? Well, something has to go into, or 25 has to go into something 25 times. So let's multiply 25 times 25. So 25 times 25 gives us 625. Well, let's try it out and see if it works. I'm going to put 625 here, and I'm going to say 25 goes into 625 how many times? And lo and behold, it is 25. So 5 is equal to the square root of 25. 5 is equal to 5. So our question was, what is the variance? And the answer is the variance is 625. I know that's kind of tough. Let's try another one. A sample with a variance of 144 has a mean of 72 and an estimated standard error of 3 points. How many scores are in the sample? So now the unknown is the number of scores. We can use the same process to figure it out. I have all the information here that we need. So I'm going to start plugging in. I know my standard error is 3, and I know that's going to be equal to 144 divided by some n that we don't know. That's the unknown. So my question to you first is, what needs to be under the square root symbol to be equal to 3? Well, that's going to have to be the square root of 9. So what into 144 is going to give us 9? Well, let's do the division. 9 goes into 144 how many times? And it is 16. And so let's try it out and see if that works. 16 goes into 144. Yes, it's 9 times. So 3 is equal to the square root of 9, or 3 is equal to 3. So the question was, what is our n? And the answer is 16. Let's back up for just a minute and talk about what it is that we mean by the standard error. Standard error's long name is the estimated standard error. We could also call it the estimated standard deviation of the distribution of sample means. It's really long, but it helps to really think about what is standard error. Standard error is an estimate of the standard difference between a sample mean and the population mean when we're looking at the distribution of sample means, this theoretical distribution that we estimate. So remember, we have this distribution that approximates what would happen if we take samples of a certain size, every possible configuration, and then plotted out all those means. And so this is the standard error is the estimated difference between any sample mean and the population mean in that distribution of sample means. We're also going to sometimes call that distribution of sample means our comparison distribution. Okay. So in part 2 of your homework, you are required to go through all of these different steps for a research scenario. You're going to identify the independent and the dependent variable, the null and alternative hypothesis. I'm not going to even read all this. We'll keep coming back to this. So I'm going to give you a study, and then I'm going to identify the independent variable and the dependent variable, and then I'm going to talk about the null and alternative hypothesis. Here we go. First of all, for the independent variable, I'm going to write down what is it that I'm going to vary in this study. Now, this is not a research study that is of an experimental design. I'm not randomly assigning people to different groups, but I am manipulating the groups that I'm looking at. So I'm looking at 2 different groups. I'm looking at the population, and then I'm looking at summer school students, this sample of summer school students. So for the independent variable, I'm going to do what is often the safe thing to do. I'm going to say the independent variable is the group that I'm looking at, either the population of all past students or this group of summer school students. And the dependent variable, the thing that I'm going to measure to see if there's a difference between my summer group and everybody else, the dependent variable is the score. That's the thing that could vary depending on what group you're in, right? Okay, so the first thing I'm going to do is I'm going to write the null hypothesis for a two-tailed test. Why is it a two-tailed test? Well, I'm going to say that I don't know in which direction the scores are going to be. Maybe they're going to be higher, maybe they're going to be lower. I'm going to have a two-tailed test to be prepared for any eventuality. So my null hypothesis is going to be the mean of my summer group is equal to the mean of the population. So I could use any sort of subscripts here, it doesn't really matter. But what I want you to notice is that I've used the mu for both of these means. And that is because when we write hypotheses, we're making a hypothesis about the population that this group came from. So I'm not making a hypothesis about these 9 students I have in front of me, but rather I'm making them about summer school students in general, okay? That's the null hypothesis, says that there's no difference. The alternative hypothesis is simply just going to be the opposite of that, which is, oh, I'm not writing very clearly. Please bear with me, is that the summer students are not equal to the population at large. That's the alternative hypothesis. As a researcher, that's the one I'm most interested in. But as a statistician, I'm going to be testing this null hypothesis. Okay, so we've got that. Before we dive into any calculations, though, I need to figure out what is going to be my critical boundary. What is the area going to be where I'm going to either reject or fail to reject the null hypothesis? My alpha is set at 0.05, and it's going to be a two-tailed test. So I've got that going on here, which means I'm going to have 0.025 in each tail. And if I look up the z-score that's associated with 0.025 in the tail, it's 1.96. So we have a negative 1.96 here and a positive 1.96 here. And so my critical values are going to be a plus or minus 1.96. If my mean of my summer group falls within either of these critical regions, I'm going to reject the null hypothesis. I'm going to reject the idea that there's no difference, and I'm going to say that there is a difference. I've put all the calculations that we need to figure this out, this t-statistic, on the right-hand side. So our t is going to be our mean minus the population mean divided by the standard error. And our standard error is figured out by finding the square root of the variance divided by n. And in order to find our variance, we need to find the sums of squares divided by the degrees of freedom, or n minus 1. In your homework assignment, you're actually given the standard deviation. So if you have a standard deviation, for example, of, let's say, 10, how do you convert that into variance? Well, variance is standard deviation squared, so 10 times 10 is 100. So keep that in mind when you are doing your assignment. You won't need to calculate the variance from scratch. You're going to be given a standard deviation, and then you're going to find the variance from that. But we don't have that here, so we're going to actually do the sums of squares and find the variance ourselves. So if I were to add up all of these scores first, well, first of all, I'm going to put, what do I need to find sums of squares? That's what I need. First thing I'm going to do is take each score and subtract the mean. And by the way, I've already figured this out. The mean is 36. So I'm going to take each score and subtract the mean. Okay, here are all of the scores minus the mean in this row right here. And if I were to add all of these up together, they would equal 0. So I know I'm on the right track. The next thing I need to do is then square all those deviation scores. Let's do that. So here are all the squared deviations, and if I add these up, my sum of squared deviations is 652. Now we're getting ready to do our variance. We have 652 divided by the degrees of freedom, which are n minus 1. We have 9 scores, so that's going to be 8. And 652 divided by 8 is 81.5. So at this point, we know our variance is 81.5. And now we can plug this 81.5 into our standard error formula. So we have the square root of 81.5 divided by our n of 9. So first let's do 9 goes into 81.5, which gives us the square root of 9.06. And the square root of 9.06 is 3.01. So we now know that our standard error is 3.01. Now that we have our standard error, we have everything we need to solve this problem. So going back, we had a sample mean of 36 and a population mean of 40. So let's plug everything in. 36 minus 40 divided by the standard error of 3.01 gives us 4 divided by 3.01. So our t statistic is, and I made a mistake already, this should be a negative 4. Our t statistic is a negative 1.33. Now we can take a look at our t statistic and evaluate it next to our critical boundaries. I'm going to draw out the normal curve, and I'm going to put my critical boundaries here and here. This is negative 1.96. This is a positive 1.96. I'm going to fill in my critical regions, and I'm going to position my t-score where it belongs. So let me kind of put some of these boundaries in here too. So it's a negative 1.33. It's below the mean. And it's more than 1 standard deviation, but not much more. So I think it's going to be about right here. Negative 1.33. Okay. So now the last thing we do is we figure out, do we reject the null hypothesis or fail to reject the null hypothesis? We would reject the null hypothesis if we had our mean in the critical boundary, but we definitely do not. And so we failed to reject. That is our decision, is failed to reject. Okay. We failed to reject the null hypothesis, which says that there is no difference. Yeah, we agree with that. There is no difference. That the mean in the population is here, our sample mean is here, but what we're saying is it's not so unusual to find our sample mean in the distribution of all possible sample means. And so we say that any difference that we're seeing here is probably just sampling error. Now, if our mean had been in one of the critical regions, we would have rejected the null hypothesis because we would have said it's so unusual to find a mean such as ours that we think that maybe there is a treatment effect, that our sample comes from a population with a different mean altogether. It's different. But we're not saying that. We failed to reject the null hypothesis in this case. In this case, there's no difference in the scores between summer school students and students in the general population. All right. If I were to write out this information, my results using statistical notation, this is what it would look like. A t with the degrees of freedom in parentheses of 8 equals minus 1.33. That's what we found. And we found that the probability of finding our sample mean is actually greater than 0.05. If it was less than 0.05, we would have rejected the null hypothesis, but it's greater than 0.05. And so this is how we would write the statistical notation for this finding. All right, so the question is, do we figure Cohen's d effect size for this t statistic result? And the answer is we wouldn't. But since I want to demonstrate how to do Cohen's d, we're going to go ahead and figure Cohen's d in this case. So our mean was 36, and the population mean was 40. That's the numerator of Cohen's d. And the standard deviation, we don't have it. We only have the variance, but in order to find the variance, we just take the square root of it to get the standard deviation. So let's do that. The square root of 81.05 is basically 9. So we have 36 minus 40 divided by 9, 4 divided by 9, which gives us an effect size of 0.44. What's interesting is, that's pretty much a moderate effect size, or it's getting close to being a moderate effect size, but we didn't find statistical significance. I'm going to give you a hint on this. Sometimes as a researcher, you do calculate Cohen's d after a non-significant test finding to see if the difference is somewhat large, and it is. Here's the reason why we probably didn't find statistical significance. We had, sorry, I'm going to cross that out because that's not it. We had an N of 9. That's a really small number. And as a researcher, if I get a non-statistical significant finding and I calculate Cohen's d just to see if maybe the difference is substantial, that just tells me that maybe I need to redo my experiment or my study with more subjects. And maybe just by increasing the N, I'll find that statistical significance. This shows that something is going on there. And it's very possible that we've committed a type 2 error, meaning there's something there that we missed. And why do we miss it? Because our N is actually too small. All right, I'm going to lead you through a couple more things real quick. I'm actually going to go very quickly on this just because I know that this video is getting a little bit long. And one of your questions on your homework is going to ask something like this. It's going to give you a population mean and it's going to give you a sample variance. And it's going to ask you some sample characteristics that are most likely to lead to a decision that there's a significant treatment effect. What I'm going to tell you is this. We are more likely to find significance when our mean is really different from the population mean. So we want that, difference between those means. But also, we're more likely to find significance, like I just showed you in the last bit, if our N is higher. So we want to have, when possible, larger sample sizes. It helps us to detect significance more. All right? A study examined whether a tutoring program made a difference in final exam scores, and here's the statistical notation for it. What is the correct decision and explanation? Well, the correct decision here is failed to reject. How do I know that? That's because my probability is greater than 0.05. Our alpha level is 0.05, and if the probability of finding our mean is less than that, then we would reject the null, but we can't here. Our probability is greater than 0.05. So what we would say is the tutoring program didn't make a difference in final exam scores. That's our explanation. So the decision is fail to reject, and the explanation is tutoring program did not make a difference in final exam scores. Okay. A study tested to see if a tutoring program increased final exam scores, and the study has this notation: should the study calculate Cohen's d? Well, we calculate Cohen's d when we have statistical significance. Do we have statistical significance in this case? We don't. Our p is greater than 0.05, which means we failed to reject the null. We don't have statistical significance. I've got one more here for you. We're going to calculate Cohen's d using the following information: population mean of 45, a sample mean of 40, and a variance of 49. Okay. So Cohen's d is equal to the mean minus the population mean divided by the standard deviation, or I should say the estimated standard deviation, or the sample standard deviation we sometimes call it. So in this case, we were not given the sample standard deviation, but no matter. We can find it from the variance. The variance is the standard deviation squared, basically. So the standard deviation is going to be equal to 7. So Cohen's d in this case is going to be 40 minus 45 divided by 7. So negative 5 divided by 7 gives us a negative 0.71. Now when we're reporting Cohen's d, we can just get rid of the negative sign. It can just be 0.71. If you put a negative sign, it's not going to count wrong, but Cohen's d is typically reported as an absolute value of 0.71. So this is getting close to a large effect size right there. All right, that's going to be it for now. I know that this was maybe a little bit fast, but hopefully it'll help you with the homework assignment. And if you have any questions, please bring them to the Hallway Conversations Forum.